Michigan Tech's FSAE is an organization where engineers of every field and discipline come together to take on the challenge of building a Formula race car. Every year, the Formula Society of Automotive Engineers, the FSAE for short, put their skills to the test in crafting a car that will not only run, but handle better and perform faster than the competition. The FSAE allows students to apply textbook theories and promote clever problem-solving strategies to real-world situations. When all is said and done, driving the car is the easiest task given to the Formula team. The true challenge of the FSAE is in creating a car that will run effectively while working under Newton's laws of motion.
Newton's first law of motion comes at the very basic level of moving and stopping a car. So the Newton's first law of motion says that a body will remain in rest or keep moving until and unless an external force is applied to it. We need external force to move the car, which comes from the engine, and we also need external force to stop the car, which comes from the brake. Newton's first law basically propels as well as stops our Formula car. Newton's second law of motion says that force equal to mass times acceleration. In our case, we want to increase the acceleration of our car, so we have two ways. Either we can increase the force or we can decrease the mass of the vehicle. For increasing the force, we have multiple options. One of them would be putting in a very powerful engine or making the car aerodynamically better so as to reduce the aerodynamic drag, or just reduce the mass by using wise materials like carbon fiber, which are really light in weight, or aluminium. So this is how we increase the acceleration of our car as per Newton's second law.
Competition for Formula SAE is tying in all of these concepts together in engineering, kind of saying how well did we utilize our knowledge of Newton's first law and Newton's second law? Did we reduce the mass enough to make a vehicle go fast? Did we increase our force by having enough friction between our tires to propel the vehicle? Did we have the right friction force to slow the vehicle down so I can corner properly? What kind of concepts did we use? And when we go to competition, we're not just judged on how well the car does, how fast it can corner, how fast it can stop, how fast it can go. We're also judged on how did we design that? What kind of equations did we use to come up with our solution to these engineering problems? We have to decide how much did the vehicle cost? Did we optimize making a component cost less by a better manufacturing process or using smarter materials? We're judged on all these kinds of engineering concepts to say how well did we apply our knowledge. Other things that we do in engineering, we do FEA, or finite element analysis, and we want to know if I can translate all these forces into my car, is it strong enough to not break down? And if I can withhold those forces with less material by doing FEA, I can reduce mass by taking it out of an object.
So friction is another key component in cars because it's essentially what propels you. If you think about rubbing two metal plates together, it's going to be pretty easy. But now if you think about rubbing a soft rubber tire up against a hard concrete surface, it's not going to be quite as easy. So that's where you really propel yourself. Another place where it's really important is trying to stop your car. Because when you are pushing down on the brake pedal in your car, essentially what you're doing is clamping your brake pad onto the metal disc. And it really wants to not spin at that point. So you just have a whole ton of friction that's going to stop your car real quick. The one case where friction really hurts us is when you're driving your car down the highway at about 60 miles an hour, say, you're trying to push your vehicle through the air. And that is really going to be kind of hard for your vehicle. So you get a lot of air friction. So you want to minimize that by designing a very aerodynamic car.
So Formula SAE is more so an engineering competition and about design and building than it is the racing of the cars, because we're all going to school to be engineers, not race car drivers, unfortunately. There's different events. Some include presenting our car and explaining all of the parts of the car and why we designed it and built it the way we did. And there's also aspects where we do drive the cars and they time these events, and the faster car does better. It's a really exciting time at competition. Everybody's running around, everybody's always busy working on their cars, preparing, setting things up, adjusting the cars, tuning them for specific events, drivers suiting up in Nomex fireproof suits. It's almost the real deal. Even though they're kind of small, it's like a big go-kart, but it is actually faster than any sports car that you can drive on the street legally. On our team, Michigan Tech's team, we have about 50 students, most of which are undergraduate students. 50 people to build one little car seems like it might be a lot, but we're designing every component of the car. We're testing our designs, improving them, trying to make our cars better, faster, lighter, stronger every year. One aspect that I really like about Formula SAE competition and our team, the whole experience, is the application of what we're learning in school. We're actually using that to make race cars, which are obviously cool. It's a rush like none other to drive what you build.